Hi everyone, let me start our talk. Our talk is Koalas. Does Koalas work well or not? We did some Koalas benchmark, so we will share how we did the benchmark and its result here. I'm Takuya, a software engineer at Databricks. I'm an Apache Spark committer and a PMC member. My focus is on Spark SQL internal and PySpark, and now I'm mainly working on Koalas project. And Shinron is also a software engineer at Databricks and a Koalas maintainer. She will show the benchmark and its result later. In this talk, I'll introduce Koalas and also Pandas and PySpark. Then I'll show some internal structure of Koalas to know how Koalas works with PySpark. After that, switching to Shinron, and she will show the benchmark. We compared the benchmark result with Dask, so she will roughly introduce Dask and show the result. Firstly, let's look over Koalas, Pandas, and PySpark. What is Koalas? Koalas was announced on April 24th, 2019 at the previous Spark AI Summit. It is a pure Python library and provides a drop-in replacement for Pandas, enabling efficient scaling out to hundreds of worker nodes for everyday data science and machine learning. It's trying to unify the two ecosystems with a familiar API and to help to make a seamless transition between small and large data. For Pandas users, it will help to scale out the Pandas code and make learning PySpark much easier. And for PySpark users, it will provide more productivity by its Pandas-like functions. Next, let's review what Pandas is. Pandas is the standard tool for data manipulation and analysis in Python. It is deeply integrated into Python data science ecosystems, and it can deal with a lot of different situations. As you can see in the Stack Overflow trends, Pandas is still growing rapidly. Python data scientists tend to start learning how to analyze data with Pandas. It works really well for small datasets in a single node, but unfortunately, it doesn't work well with bigger datasets. Data scientists have to learn PySpark or other libraries if they want to handle bigger datasets. Okay, then, what is Apache Spark? Spark is a de facto standard unified analytics engine for large-scale data processing. It supports streaming, ETL, machine learning, and so on. It provides PySpark as an API for Python, as well as APIs for Scala, Java, R, and SQL. Koalas data frame follows the structure of Pandas and provides Pandas APIs. Also, it implements the concept of Pandas index or identifier. For example, Koalas provides series or index as well as data frame, and it can pick up some rows based on the index values or their origin index number. On the other hand, PySpark data frame is more compliant with the relations or tables in relational databases. So the PySpark APIs are rather only essential to perform relational operations. Even if Koalas objects have the same APIs as PySparks, the behavior will be different since it follows Pandas behavior. Koalas translates Pandas APIs into a logical plan of Spark SQL, and then a plan will be executed by the Spark SQL engine. The execution will be done lazily so that Spark SQL's optimizer can come in. When a user tries to show, collect, or store the data, the whole plan will be passed to the Spark SQL engine. Then the engine optimizes the plan, compiles, and executes it. Then let's dive into the Koalas internal structure. Here, I talk about the internal structure named internal frame and how it works between Koalas data frame and PySpark data frame. Internal frame is internal immutable structure, and it holds mainly 4 types of data. The first one is the current PySpark data frame. The whole operations are based on this PySpark data frame. Secondly, it manages PySpark column objects for both index and date columns separately from PySpark data frame. This is used for maximizing map side operations without shuffling, as well as the mapping between Koalas index or date columns and PySpark columns. The column objects are derived from the PySpark data frame and contain the updates from it. For example, df+1 don't need to create a new PySpark data frame, but only updates the columns as col+1 for each column. We can combine the column updates and the underlying PySpark data frame to calculate the result later. Also, it manages index names and data column names because Koalas index names or data column names are not always equal to PySpark data frame's column names, since it can be int, float, etc., as well as string, and also it can be multi-level values like tuples, whereas PySpark's column names must be only strings. D-types are the other metadata. D-types in this case are equivalent to Pandas D-types, not Spark's date types. This is because there are some Pandas D-types which can't be represented by only Spark's data types. For example, Pandas has categorical D-type, period D-type, which are not supported in Spark SQL, or there are nullable int, float, string, Boolean types, in addition to the normal corresponding types. Last but not least, it provides the way to convert from Pandas data frame to PySpark data frame and extract metadata. Conversely, the way of conversion from Koalas data frame to Pandas data frame is provided here. It combines the PySpark data frame and columns, then convert it to Pandas data frame. The directly converted Pandas data frame could have different column names or D types, so it fixes them with the other metadata. The result must be like the expected Pandas data frame. The basic structure is like this. Koalas data frame has internal frame in it, and internal frame refers PySpark data frame and holds some metadata like Spark columns, index names, column names, D types, and so on, as I mentioned. When a user calls some API, Koalas data frame updates PySpark data frame and metadata in the internal frame to behave like the corresponding Pandas API. and creates or copies the current internal frame with the new states, then returns a new Koalas data frame. Sometimes the update of PySpark data frame is not needed, but only the update of metadata is needed. New structure will be like this. For example, renaming column names or index names doesn't need to use a new PySpark data frame. Or df+1 I mentioned before also doesn't need a new one. It can be done only by updating the Spark columns instead. Koalas tries to avoid creating a new PySpark data frame if possible, so that Koalas can easily calculate something like df1 plus df2. If the underlying PySpark data frames of df1 and df2 are the same, it will be just a Spark column operations. Otherwise, we need joins to combine the two PySpark data frames. In any case, Koalas data frame will never mutate internal frame, but creates or copies the internal frame to keep it immutable. This is a rough overview of Koalas data frame. I hope this helps you understand what's happening in Koalas. Now let me hand it over to my colleague, Shinron, who will walk through the benchmark.
Thanks, Takuya. Great introduction of Koalas and its internal. Then, does Koalas work well? We've conducted a benchmark against Dask to answer that question. What makes Dask special? Dask is a parallel computing framework. It's written in pure Python, so it can leverage the excellent Python ecosystem. It parallelizes code bases like NumPy using blocked algorithms and task scheduling. Blocked algorithms can evaluate a large problem by solving many small problems. Then, what does task scheduling mean? A task represents an atomic unit of work to be run by a single worker. A task graph is built from parallel collections. A scheduler executes task graph on parallel hardware. There are single machine scheduler and distributed scheduler. Dask is great. How is Dask different from Koalas? First, they have different execution engines. Koalas is built on top of Apache Spark, which is a unified analytics engine for big data. Dask itself is a graph execution engine. Second, Koalas aims to provide a single code base that works with both Pandas and Spark. If you are already familiar with Pandas, you can be productive with Spark immediately. Dask aims to scale Pandas workflow. Third, in Koalas, query plan is an entry point to understand the query execution, whereas Dask has task graph and task scheduler, as we mentioned at the beginning. Last, Koalas implements Pandas data frame APIs. Dask has parallel collections, such as array, data frame, and bag. Clearly, Dask and Koalas have many differences, but they can both scale Pandas. Wouldn't a performance comparison be interesting? So we conducted a benchmark. How did we set up the benchmark? The dataset contains about 150 gigabytes of taxi trip records. We benchmark common operations such as basic statistical calculations, joins, and grouping. These operations were applied to the whole dataset, then the filtered data, and finally, the cached filtered data. Filtered data is 36% of the whole data. In this way, we can understand the impact of lazy evaluation, caching, and related optimizations in both systems. The scenario used in this benchmark was inspired by Jonathan's big data benchmarks. Then, where did we run the benchmark? The benchmark was run on top of Databricks runtime. We ran it on a single machine, and then in a cluster. The cluster has 4 nodes. It has the same total memory as the single machine. We ensured both Dask and Koalas to run in the distributed mode. Here's an overview of benchmark results. Koalas outperformed Dask in the benchmark. Considering simple average, in the local mode, Koalas is 4 times faster. In the cluster mode, Koalas is around 8 times faster. Koalas APIs are written on top of PySpark, so the results would apply similarly to PySpark. Are you interested in detailed results? Let's look at some plots. Each bar in the plots shows the execution time for an operation. The ratio of Dask's execution time to Koalas' execution time is annotated per operation. For example, 2x means Koalas is double as fast as Dask. Plots on the left-hand side are for local mode, whereas plots on the right are for distributed mode. First, let's look at the operations that apply to the whole dataset. In local mode, Koalas was on average 1.2 times faster. The operation count when joining was 17 times faster. In distributed mode, Koalas was on average double as fast as Dask. Count index operation was 25 times faster. Then we apply the same operations to the filtered data. Filtering is computed together with the operations lazily. In local mode, Koalas was on average 6 times faster. The count operation was 11 times faster. In cluster mode, Koalas was on average 9 times faster. The count index operation was 16 times faster. Finally, we cached the filter data, then apply the same operations. Here, the data was fully cached before measuring any operations. In local execution, Koalas was on average 1.4 times faster. The operation count when joining was 6 times faster. In cluster mode, Koalas was on average 5 times faster. The count index operation was 28 times faster. Are you wondering why Koalas is best? As we mentioned above, Koalas is based on Apache Spark. At the core of Spark SQL is the Catalyst optimizer. On top of Catalyst, we have code generation to generate optimized bytecodes at runtime. They both accelerate Koalas significantly. To understand the influence of Catalyst, we look at the mean calculation on the filtered data. We filter down the original data by tip range and then calculate the average value. The query plan before the catalyst optimization uses brute force to read all columns, and then performs projection multiple times with the filter in the middle. This is inefficient because it needs reading more data, spending more time on I/O, and performs the same projections multiple times. The query plan becomes much simpler after catalyst optimization. Now, it only reads the columns needed for the computation and filters data in the source level that saves memory usage. Let's move on to the code generation. We take two operations on the filtered data for examples. Without code generation, mean calculation takes 8 seconds, and count when joining operation takes 27 seconds. With code generation, calculating the mean takes 1 second, and the join count operation takes 2 seconds. It's a huge improvement. The benchmark results demonstrate that, first, SQL optimizers, such as the one in Spark SQL, can improve performance of data frame APIs. Second, caching accelerates both Koalas and Dask significantly. Third, in the benchmark, Koalas outperforms Dask in most of use cases. I want to add that different projects have different focuses. Even though the benchmark we ran was reproducible, and we tried our best to be fair throughout the process, there might be unconscious bias. The main goal of the benchmark is to study SQL optimizers' influence to data frame APIs. If you'd like to know more about the benchmark, please check out the reference blog post. All right, that's the end of our benchmark section. Then, what's new with Koalas? Since Spark AI Summit 2020, Koalas has released 9 versions. Let's take a look at main changes. Plotting support is improved by implementing pie, histogram, and box plots with Plotly. Plotly is our default plotting backend now. Basic extension dtabs are supported, such as categorical dtab and int8 dtab. More types of index are introduced, such as datetime index and int64 index. API extensions are supported, so you can register your custom accessors to data frame, series, and index. Type hints support are enhanced by allowing Pandas instances and column names in the return type. There's one exciting news. We are going to port Koalas into PySpark. With the Pandas API layer on PySpark, users can leverage their existing Spark cluster to scale their Pandas workloads. They can also easily switch between Pandas APIs and PySpark APIs. If you'd like to know more, please check out the Jira ticket. That's the end of Koalas updates. Thank you so much for having us. Takuya and I are happy to answer any questions you may have.